to begin this discussion, uh, it's probably best just to show a quick little PowerPoint, although we're going to go into the software in just a moment. But with Workplace Planner, the focus is to link an Excel spreadsheet of work tasks that people perform with a layout drawing where they perform the work. So we're essentially linking an operator's work process, their circle of work. They do a task at a location, they walk somewhere. They do a task at a location, they walk somewhere. And they may do this over and over and over in many cycles with a scaled layout drawing where the work is performed, so that as we modify the layout, we can see the impact of walking on that person's cycle time, on their process flow. And by using the diagrams that Workplace Planner generates about how the operators walk through the facility, it really helps us understand how we can improve the layout to reduce the walking component. It probably goes without saying that Workplace Planner is very layout centric in its analysis. In other words, if you were just going to do a process analysis where an operator stands at a location and never walks, Workplace Planner probably isn't the solution for you. Workplace Planner is best applied to situations where the operator does do quite a bit of walking in their overall work cycle. So in the drawing that we're looking at here, this is a classic output of Workplace Planner. We have an AutoCAD layout drawing and we have text labels where work is performed. We load a spreadsheet of process tasks that are in sequence and have a time specified. And as the operator goes from task to task to task, where some of those tasks may require the operator to perform them at a different location, the program will automatically draw a line to that next location, show an arrow in the direction of flow, show the distance of the walking, calculate that into a time, and add that to the operator's overall cycle time. So as a result, we end up with an analysis that may look something like this. Here I actually have an operator and I have a hoist where the operator uses the hoist, so I can have multiple operators, one or multiple operators, and I can also have one or multiple pieces of equipment. And that equipment can be stationary or it can be dynamic. Now you may ask, why would the equipment, if it's stationary, or even to some extent if it's dynamic, in other words that it moves, be relevant for Workplace Planner analysis? And that is because operators and equipment can interact in such a way that they block one another. That means that an operator may have to wait for a piece of equipment to be available or wait for another operator to be available if those two operators need to do a task synchronously or essentially at the same time. So that creates what's called an internal delay. So what we're going to be looking at here is we can see this operator here. We see that there's a walk distance for their total cycle. We have a total cycle time. What percent of time are they walking? What percent of the time are they doing value-added work? What percent of the time are they doing non-value-added but necessary work? What percent of the time are they doing non-value-added work? Okay, and this is a round off error on the -1 here. And then what percent of the time do they have an internal delay and what percent of the time do they have an external delay? That's what ID and XD mean. So internal delay would mean that the operator is actually waiting on a resource. So you can see in this case, the operator waits on the hoist becoming available 4% of the time. The hoist in this case waits on the operator 88% of the time. Obviously, we don't really care about how much time the hoist is waiting, unless of course the hoist is a critical resource. And we have a classic man-machine problem where we may have multiple people working to keep that machine busy. External delay would be a situation where the operator cannot begin work or the operator may end work early and have to wait until their next cycle comes up. So before they could start work again. So external delay is time before they start or after they end, before their cycle can repeat. That would typically be a case where I have multiple operators and one of them has to wait for the other one to finish before they can do the cycle. So that's essentially what Workplace Planner is calculating. This is an example of a Workplace Planner input file. One of the things you'll see how Workplace Planner is designed is it's targeted to really sit between AutoCAD and Excel. So I have an Excel spreadsheet of routings, and that could be authored, directly in Excel. You can do some authoring in Workplace Planner, but the interface really isn't ideal for that. And this file could also be generated externally by another application. What we're looking at is we have multiple, operator tasks or steps. All right, my mouse is messing up here. And we see operator one, operator one, operator one, walk, process, M is a processing task, W is a walk task, it's a manual walk task, or manual processing task, sorry. W is a walk task, M is a manual process task. Now, we could specify in column D an actual time, or we can put in a predetermined language, such as MODAPS in this case. Now, one thing that's interesting about a predetermined language is that while the processing task, the manual processing tasks, code M in column B, may reference MODAPS codes, they're used to compute an actual time. And we actually see a time in column K. So the software parsed the MODAPS codes and generated the time for that task. That's just classic predetermined time parsing. However, in the case of column D, whatever the, for walking tasks, whatever the operator enters, in this case, W12, is really irrelevant. Why do I say that? Because the software will compute the walk distance from the drawing, figure out what the proper MODAPS code would be to walk that distance, and then it automatically updates or replaces whatever was in column D with the appropriate MODAPS code, and then of course computes the actual walk time shown in column K. So J, K, and L here off on the right are good examples, or J and K in particular. Actually, L is a value-added, non-value-added definition. But J and K are computed by the application, the time that's computed and the distance that's computed. And in some cases, the distance is computed time. It comes from a computed distance from the drawing. Column L represents whether the task is value-added or not. Now, by definition, walking is non-value added. So the software is automatically going to populate column L's walk rows with a 0. However, the operator can put in the value or non-value added, but necessary. In this particular case, you can see row 3 is a MODAPS code to obtain a hub. Now we're going to assume that that's a non-value added but necessary task. So we enter a /100. If it was a value-added task, it would be 100. So you're starting to get, hopefully, that handle that it's the value / non-value. So as I come down here to row 16, you can see obtain overhead multi and bring down something 50% value-added / 50% non-value-added but necessary. Now remember, the / is non-value-added but necessary, or non-value-added required. What that means is you don't specify non-value at all directly. It's always the remainder. So if we look at row 5, I have 50% in there. There is no /, so there is no non-value-added but necessary value. The software will always take the remainder of the value and non-value-added but necessary and make that non-value. Okay, so first row is 100% non-value. Second row is 0% non-value and 0% value. It's 100% non-value added but necessary. Row 3, 100% non-value. Row 4, 50% value added, and then the remainder is 50% non-value. The next row, of course, 100% non-value added but necessary. The next 2 rows are 100% non-value. You get the idea, hopefully. You can see we do have some rows here, place onto dust shield, aligning hole, ABS units, feed ABS wire through dust shield. Those 200s represent the fact that those tasks are 100% value added. So it's really not super complicated to define this list of tasks. You can see they're all listed for the operator. We can also see that as we go down towards the bottom of this list, rows 30 and 31 and 32, and I apologize for those being right there at the bottom, but hopefully you can see them okay. We have another interesting situation. You'll see me do this in a moment. Row 31, operator 1 and the hoist are going to both need to be available before the next line of this process list will be evaluated. What do I mean by that? I basically mean that all these operator tasks have to be performed, and this one hoist task has to be performed before the operator and the hoist are both available. Now, they will occur concurrently. In other words, each operator works in parallel. So the operator and the hoist both start out. Initially, the operator 1 is walking, doing a W12, and the hoist is also being moved W12. Now you can see at this point, the hoist is available, but the operator is still busy. So the hoist is going to wait on the operator until the operator does all these tasks until row 31. Once all the rows have been processed prior to row 31, then the software will process row 32 and beyond. In other words, at that point, it goes parallel again. Operator 1 does their thing, the hoist does its thing. But obviously, there's an internal delay. Now, by looking at this spreadsheet, it's pretty obvious that once they start off and both do their walk 12 motion, the hoist has no other tasks prior to this synchronization on row 31. So the operator, the hoist is going to wait for this whole time until the operator is available. And as I go back to the summary, you can see the hoist waiting on the operator. Totally makes sense. Okay, so the other thing the software is doing then is, since I did classify time for the tasks, and I am identifying time spent walking, and I am identifying situations where one resource or operator has to wait on another, we end up with a situation, and I'm also classifying when tasks are performed, whether they're value added or non-value added, but necessary or non-value added, or whether they're internal delay or whether they're external delay. You can see pretty clearly why I can generate this bar chart, or these set of bar charts, one for each resource, because I'm actually able to show what percent of the cycle time is spent by each resource, operators and machines, in these various areas. The other thing I can do is generate a report. And when we generate the report, we're actually using our process symbology, our operate, our transport, our delay, our inspect, right? our store. Those are the classic industrial engineering process symbols, right? So delay would be internal, external delay. Inspect is another thing I can specify when I'm processing, whether I'm inspecting or not. I'll show you where that gets entered. And then also whether I'm in storage or essentially being held up in a bin waiting to be processed. So this allows me to take these different steps, identify the process symbology, where they're performed, and this is just a user-defined location. It's essentially going to be represented in the AutoCAD drawing as a text label on a certain layer of AutoCAD. So table-hub will be an AutoCAD text object in the AutoCAD drawing on a certain layer. Table-fixed will be an AutoCAD text object. Mid.wc will be an AutoCAD text object located somewhere in the drawing. The software, Workplace Planner, will look at where it is and automatically draw walk lines to and from those location spots in the drawing and calculate their distances. And that's how distance and time is computed off on the right, hence our summary report. Now, this is a great example of how Workplace Planner is used for what we call static workplace analysis, which means that while the operator and the tools are moving, when the operator is performing the work is stationary. We're going to take a quick overview look at a moving product study, essentially. What that means is that while the operator is working on the product, the operator is also moving. Okay, this is a very unique situation typically used in the automotive industry, where on a moving assembly line, the operators, when they start a task on the vehicle, they may stand on a flat top conveyor and move with the product, which means that when they leave the vehicle, they're not in the same spot they were in when they got to the vehicle. Now, this is pretty important in a walk past study, right? That's often referred to as a scrolling analysis. Is that when I'm calculating operator walk distances, I need to know where the operator is at every point in the cycle time. So this is a little more complicated. The software Workplace Planner was designed to handle it, and we'll see how it works in doing this. This is a great example of a drawing showing you the operator walking from different bins and storage areas for parts in the workplace to the vehicle, and then leaving the vehicle and going and getting other parts, and then going back to the vehicle, and so on. Of course, as before, we have an operator on the right, we have an operator on the left, we have a cycle time, we have a walk time, we have a value added and non-value added analysis.